In the melody of singing harp strings, we can begin to explore the science of musical sound. The strings are silent until they are plucked. Then they move back and forth very rapidly. When something moves in this way, we say it vibrates. A xylophone is also silent until its wooden bars are made to vibrate. A flute sings its song when air inside is made to vibrate. Harp strings vibrate at different rates to produce the tones we hear. This long, heavy string vibrates about 65 times in 1 second. This is near the lowest tone we can hear. We cannot hear a sound when the vibrations are less than 20 a second. This short, thin string vibrates more rapidly, over 1,000 times a second. We can hear this tone very easily. The normal human ear can hear more than 15,000 vibrations a second. Scientists use the word frequency in describing sound vibrations. Low-frequency sounds have only a few vibrations in 1 second. High-frequency sounds have many vibrations in 1 second. Musicians have a special name for the highness or lowness of a sound. They call it pitch. This low-frequency sound has a low pitch. This high-frequency sound has a high pitch. Another source of sound is the vibration of metal in this device called a tuning fork. When the prongs of a tuning fork are made to vibrate, the tuning fork always vibrates at the same frequency. A harpist uses a tuning fork to tune the strings of the instrument. She listens to the tuning fork to compare its sound with the sound of the harp string. If the instrument is not in tune, she will tighten or loosen the strings to make them vibrate at the same frequency as the tuning fork. A pointer attached to a tuning fork draws a picture of the sound it is producing. We can use this picture to learn some important ideas about sound. By counting the number of waves drawn in 1/2 second, we can discover the frequency of the sound vibrations. In this part of the drawing, there are 30 waves. This tells us that the frequency of this tuning fork is 30 vibrations in 1/2 second, or 60 vibrations in 1 second. Scientists have other ways of seeing and measuring sound vibrations. This instrument is called an oscilloscope. It draws a picture of sound vibrations on a screen, which is like a television receiver. This picture is similar to the one drawn by the tuning fork. An oscilloscope can show us many things about sound vibrations. it can show the difference between a low-pitch note and a high-pitch note. Let's compare the oscilloscope waves of a low-pitch sound and a high-pitch sound. This high-pitch note has twice as many vibrations or peaks in its wave as the low-pitch note. See and hear a gently plucked harp string as it vibrates. Hear the same string plucked with greater force. Using an oscilloscope, we can observe differences between soft sounds and loud sounds. We find that loudness depends on the amount of energy producing the sound vibrations. An oscilloscope can also show the difference between music and noise. Noise looks like this. Music looks like this. Look for differences between noise waves and musical waves. The regular patterns of music have differences too, even when sounds of the same pitch are played on different musical instruments. Here is middle C on the harp. Here is the same note on the flute. Middle C sounds different on each instrument, yet the pitch is the same. Musicians all over the world have agreed to tune their instruments to the note A at 440 vibrations per second. This makes middle C 261 6/10 vibrations per second. This tuning fork produces a middle C of exactly 261 6/10 vibrations per second. Let's discover why middle C has a different sound on a musical instrument. Here is a tuning fork wave. It has the same number of high peaks as the harp wave, because the sounds have the same pitch. The tuning fork wave has smooth sides because its sound contains only one frequency called the fundamental. The harp wave has jagged sides because its sound contains the same fundamental plus other higher frequencies called overtones. Listen to the two sounds when they are played together. Next, let's compare the sound wave of the tuning fork with the sound wave of the flute, as they both produce middle C. Again, the jagged sides of the flute wave show that the flute also has overtones. Overtones make it possible to tell one instrument from another by giving each instrument a different sound. Now let's hear how overtones can turn a few simple notes into the stirring music of a marching band.